Hello everyone, I'm Haimin from Nanjing University. Today I will talk about broadcasting competitively against adaptive adversary in multi-channel neural networks. This joint work with an advisor, Chaodong. We consider single hop network with n nodes, and nodes communicate over shared medium containing C channels. Time divided into synchronous runs, often called slots. So the time complexity is measured by the number of slots. Each node have a half-duplex transceiver. So at each slot, it can either send on a channel, or listen on a channel, or remains idle. A node cannot send and listen simultaneously. Also, it cannot work on multiple channels in one slot. Lots of radio devices are powered by battery and are able to switch between active and sleep states. So we also care about the energy complexity, measured by the number of channel accesses. Specifically, sending or listening for one slot costs 1 unit of energy, while idling incurs no cost. For each slot, only nodes listening in the slot will get a feedback. In the single channel setting, in other words, if C is 1, the feedback is determined by the number of sending nodes. If no node sends, the feedback will be silence. If exactly one node sends, our listening node will receive the message. When at least 2 nodes send, the feedback will be noise. Now back to the multi-channel setting. Since there is no interference among channels, so for each channel, its status depends on the number of nodes sending on that channel. And only nodes listening on that channel will receive status as a feedback. For example, 2 nodes send in first slot, but blue node is only 1 send on channel 2. So the pink node listening on channel 2 will receive a message from the blue node. The shared nature of wireless medium makes it vulnerable to jamming. So in this model, an adversary called Eve also participates in execution by jamming, but she cannot send any meaningful messages. As long as the channel jammed, nodes listening on it will receive the noise. And if a node receives noise, it cannot distinguish whether the noise is due to message collision or jamming or both of them. For example, if in second slot Eve jam channel 2, then the pink node will hear noise now, while the green node on channel 1 will still hear the message. Each slot, Eve can jam any set of channels, for example, jam all channels in the third slot. And Eve is adaptive, so she's given all past execution history to decide which set to jam in current slot. Clearly, we need to put certain restriction on Eve, and then develop corresponding algorithms. Notice Eve also consumes energy when she injects interfering signals. In view of this, a recent and interesting way, resource competitive analysis is proposed. The only restriction of Eve is the total amount of jamming. Specifically, we assume jamming one channel for one time slot costs 1 unit of energy, since the expenditure for sending, listening, and jamming are often in the same order. The budget of Eve is denoted as capital T, which is unknown to nodes. With the algorithm, no matter what the jamming strategy Eve adopts, the maximum cost is at most some function rho of T plus some term tau. Here, rho is a function of T and possibly other parameters such as N and C, which capture the additional cost due to jamming. While function tau is the cost of the algorithm when Eve is absent, so tau should not depend on T. Our main goal is to minimize function rho and keep tau small if possible. So we consider T is large when compared with N or C. We are especially interested in the algorithm whose cost of each node is little of T, which shows to disrupt nodes from solving the problem, Eve must spend much more energy than each node. The problem we focus on is broadcast, in which a source node wants to send the message to all the other nodes. Specifically, all nodes should receive the message and halt. and we want to minimize the additional energy cost and the addition time due to jamming. We're also interested in scenarios that n is unknown. For example, network organized in ad hoc mode without infrastructure often cannot provide knowledge of n. Before the execution, each node knows whether it is a source and the number of channels, C. Here's the result. All these are Monte-Carlo algorithms and hold with hyperpopulation in N. In 2011, King, Saya, and Yang developed first resource competitive algorithm. Later, Gilbert et al. Gave an algorithm that each node holds within O of T slots, and each costs soft O of square root of T over N. This algorithm works even N is unknown to nodes. Last year, we showed having multiple channels allows the linear speed up in runtime, while the cost remains unchanged. But our algorithm only works when C is O over N and can only tolerate and obliterate the adversary. There are also some lower bound results. The time complexity part is obvious, since Eve can jam all channels during the first T over C slots. As for the energy complexity, Gilbert et al. Proves there must be a node with cost root of T over N, showing their algorithm is optimal up to Polylogue vectors. So our motivation is to close the gap by considering an adaptive adversary and designing algorithms that work for arbitrary NC values. Besides, is there a more competitive algorithm in the multi-channel setting? In this work, for the upbound, we developed two algorithms that work for any NC values and can tolerate an adaptive adversary, both with time O of T over C and energy cost root of T over N. The first algorithm is very simple, and the second algorithm works even N is unknown to nodes. We also answer the second question by proving a lower bound, root of T over N in the multi-channel setting. So our algorithms achieve near optimal energy complexity and optimal time complexity simultaneously. We first introduce our first algorithm, MultiCast. Before introducing the algorithm, we show a framework that is used by all these algorithms. An algorithm should group slots into consecutive epochs, execute a jamming-resistant broadcast scheme, and check whether to halt after each epoch. The broadcast scheme should be effective and competitive, so each node learns the message while spanning asymptotically less than Eve. As for the counting criteria, it should be reasonable, so each node should have received message when they decide to halt. Besides, to stop nodes from halting, again, Eve is forced to spend much more energy. Finally, since node does not know T, the usual approach is to let epoch length grow exponentially. So for both nodes and Eve, the total energy consumption is dominated by that of last epoch. So later, we only consider one fixed epoch. Our first algorithm uses a parallel broadcast, often called as epidemic broadcast. Assume node U is still active at the beginning of epoch I. In each of the R slots of epoch I, it will hop to a channel chosen uniformly at random and choose to send and listen each with probability P. If you decide to send, you will send the message when MU is true and send a beacon when MU is false. Here, MU is a Boolean variable, indicates whether it has known the message. Before the execution, only the source node sets its M to true. We use X to denote the number of silent slots you heard during the epoch. At the end of epoch, you will halt if X is at least H, where the threshold H is half the expected times of listening. Finally, we set proper values of R and P. In analysis, we focus on answering two questions. Firstly, why does the work-class scheme work when P is root C over NR? Secondly, why is this halting criteria correct and competitive? Let's begin with the first question. In a single channel setting, the core idea is to broadcast sparsely. For example, consider N is 2, and we name the source node Alice and the other node Bob. If Alice sends in root R random slots and Bob listens in root R random slots, then by an argument like birthday paradox, there must be a successful transmission, even if you jam constant fraction of slots. Also, previous work has shown the expression for any n. Surprisingly, when n is larger, the cost of each node is smaller. When C is n over 2, roughly speaking, there are 2 nodes in each channel on average. So the right property is still 1 over root R, but we give another expression, root of C over NR, and show another dimension of birthday paradox. From now on, we fix any slot and assume each node can work on T channels simultaneously, but with a cost T. Compared with single channel setting, if we have C channels, the probability should be multiplied by a root C factor. Then each pair of nodes will meet on at least one channel with counter probability, which means optimal single channel analysis would work again. Obviously, root C over NR is the optimal expression for any NC values. Next, we focus on the halt criteria. Recall for each node U, it counts the number of sensors heard at X and halt if and only if X is at least H. We will fix node U. If jamming is weak, we have already shown all nodes will know the message. Otherwise, each node will not halt, since the jamming is severe. So expectation of X is less than the threshold. Compare the two properties together, our criteria is correct. Here we use the following definition with 2 parameters. If there are more than A fraction of slots, that each with more than B fraction of channels unjammed, then we say the epoch is AB weakly jammed. For example, the picture shows an epoch of 6 slots, and we say it is 4/6, 3/4 weakly jammed. As for competitiveness, we show if the epoch is 0.8 weakly jammed, then expectation of X is large, so each node should halt. We will prove the competitiveness by bounding the following by bounding the probability of the joint events, X below threshold H, and the epoch is weakly jammed, or sometimes bounding the conditional probability. We need some extra definition. Let QK be the set of unjammed channels in slot K. GK be all nodes behavior in slot K. Then the indicator XK is determined only by GK and QK. In our algorithms, nodes behavior in different slots are independent. When Eve is oblivious, the jamming vector Q is fixed before the execution. So X1, X2, till XR are independent. And the expectation with sum X is also large. So we can use concentration inequality like Chen bound to bound the conditional probability. However, adaptive adversary can observe nodes behavior and determine the set QK in the K slot. For example, Q3 can be dependent on G1 by this definition. Also, X1 indicating whether you hear silence in slot 1 depends on G1. So X1 and X3 are not independent. We are deprived of the useful tool, show no bound. Even when condition on a fixed Q3, the distribution of G1 may be distorted, which means we have no guarantee on expectation of x1. In this work, we use a coupling technique to resolve the dependency issue. By law of total probability, we can first turn to bound the series probability that x is less than h, and the jamming vector q equals to a fixed q. Now, fixed q that is weakly jammed. We create a coupled process and relate x to some variable yq in the coupled process. Specifically, in the imagined process gamma q, all nodes run same algorithm, and Eve jam obliviously using the fixed vector q. Then y is the number of signals heard by you, and y is the sum of independent indicator variables. We couple x and y in a third process by using identical nodes behaviors. The key point is in each slot k, when the actual jamming vector q is equal to the fixed q, then xk are always equal to yk. So we can turn to bound probability that y deviates much from its expectation. However, there is still a problem. There are nearly 2 to the RC kinds of vector q, so the sum of this failure probability is too large. Actually, we can direct couple x to y if we underestimate x and use a more complicated version of coupling. Our second algorithm works even n is unknown to nodes. When the value of n is unknown, the principal issue is how to properly set one node's working probability. A natural approach is to get n. Specifically, the epoch I contains I phases now. Different phases may have different working probabilities, but the probability is fixed within one phase by assuming n is 2 to the j in the jth phase. However, the broadcast succeeds only when j is close to log n. Even worse, when the probability is too small. Most of feedback received would be silence if Eve does not jam or jam very weakly. So nodes may halt in a phase that broadcast fails, which means the criterion becomes incorrect. Another challenge is related to competitiveness. The total number of slots in phases that achieve broadcast should be some sufficient large fraction of the number of slots in whole epoch. This ensures Eve cannot gain advantage by only jamming in certain phases. We provide our second algorithm, MultiCastAdv, which adopt Gilbert framework. Now an epoch contains multiple phases, each with R slots. Each node U independently adjusts its probability PU based on the feedback it receives. Before the first phase of epoch I, the probability is initialized to a very small value. After each phase, PU is multiplied by a factor of 2 to the maximum between eta minus 1/2 and 0, where the fraction eta is the number of silent thoughts heard by you over the expected time of listening. The way updated P seems strange, but has two nice properties. Firstly, you have to keep jamming heavily to prevent PU from reaching the optimal value. Besides, PU and PV are always close at each phase. To bound the difference of node probability, we show no matter what the jamming vector Q is, the number of silent thoughts X is always close to its expectation. But in previous algorithm, we only show X is larger than some threshold when the jamming is weak. This is a big difference. So handling adaptivity by coupling becomes more involved. The last part is about lower bound of energy complexity. In the single channel setting, previous work has shown in one-to-one broadcast, either Alice or Bob will cost root T. And then show one-to-one broadcast can be reducible to the anode broadcast. Specifically, Alice simulated the source, and Bob simulated all other nodes. It's easy to see this reduction also holds in the multi-channel setting. So the only thing left is to prove root T lower bound for the one-to-one broadcast in the multi-channel setting. We first introduce the strategy of Eve in each slot. For each channel, if the probability that Alice successfully transmits to Bob exceeds 1/T, then Eve will jam the channel. The success probability is a product of the probability Alice sends and the probability Bob listens on that channel. To prove lower bound for any algorithm, we only need to consider all oblivious algorithms. Here, an oblivious algorithm means the sending and listening probability in each slot should not depend on the actual behavior in past slots. In other words, they should be decided before the execution. So why we only need to consider oblivious algorithm? This is because any path to a leaf of the decision tree A corresponds to an oblivious algorithm. So A can be seen as a convex combination of these oblivious algorithms. Moreover, at least one oblivious algorithm is as good as A in both success probability and expected cost. Finally, according to whether Eve will ever deplete its energy, we consider two scenarios and prove lower bound respectively. In summary, we design fast and competitive broadcast algorithms using activated broadcast with proper working probabilities. In analysis, to handle the adaptivity of the adversary, we couple the real execution with other carefully crafted executions. We also prove energy lower bound for the broadcast problem in the multi-channel setting. An open question is, can we prove an energy lower bound for an oblivious adversary? Since all energy lower bounds are proved for an adaptive adversary. Thank you for attention.